In this example, we're going to look at parallelizing a piece of work to calculate a set of numbers and the factorial of those numbers. So this is a slightly contrived example to generate something that actually takes some amount, a measurable amount of CPU time, and basically does a series of calculations. So the factorial of a number is that number multiplied by all the numbers below it. So factorial of 3 is 3 times 2 times 1, and the factorial of 5 is 5 times 4 times 3 times 2 times 1. So in this case, what we're doing is we're initializing an array of length 500,000, and we're creating two arrays of that length. One is the n values, which is the number that we want to calculate the factorial of, and the second one then is the resultant factorial of that. We go through, we initialize these arrays, we set them all to the same number, so we're duplicating work here, but again, that's, as I say, a contrived example. So we're setting them all to be calculate the factorial of 50. We're using unsigned long as these very quickly become very large numbers, 50 times 49 times 48 and so on. We initialize the factorial result array with 1, and then for each element in the array, we perform the calculation. So we start with our element in the array, so that's 50 for every position. Continue while our x value, which is our counter, is greater than or equal to 2, decrementing it each time, and times the current result in the factorial array by x. So it would be 50, it's already 1, so it's 1 times 50, and then that will be 50 times 49 times 48 times 47 and so on. At the end, just as a sanity check, we output the result of what's in n0 and fac0, so we see the factorial of one of the results in there. So let's compile this. No parallelized code at the moment. And let's time it. Okay, so we ran through. You can see there it's given us a number. There's a lot of digits in there, and you see why we used unsigned long, and it's taken 0.2 of a second to do that. So that's a measurable amount of time. Interestingly, if we run it again, you will see that it takes significantly less time because it's now cached within system memory. So the first time we run it, this total amount of time includes loading it from disk into memory. It's now cached in memory, so actually this is more realistically the execution time. So 0.07 of a second, 700th of a second. So fairly quick, but obviously what we're going to do is have a look at parallelizing this in order to speed it up. So let's have a look at how we could do that. So we're just going to copy this and then paste it in. So this is the parallel version of our code. So what do we need to do? We need to include OMP.h, and we need to decide what it is we want to parallelize. So these initializations, we need them to happen once. We want the initialization array to run through. We could parallelize this, but it's instantaneous. It's hardly going to take any effort. Clearly, we need to look at these loops here. Now, these loops are independent calculations. The factorial, the outer loop is an independent calculation. Each item in the array is calculated utterly independently of the other one. So this is what we term as embarrassingly or pleasingly parallel. We can split this, and there's no need for one value to reference another one. However, this loop is a little bit more complicated because what we're doing is we're multiplying the previous result. So best to leave this one alone, and we come on back to this later in our discussions. What we're going to do is we're just going to parallelize this loop. So we have currently 500,000. What should happen is that each 50,000 should be handled by each thread. So form a parallel region, execute the for with it, and go through and do that. Okay, so GCC, remembering to link in OpenMP, parallel. And now let's execute this. So we were on 0.2 of a second on the first run, 0.07 of a second. Okay, 0.18 of a second, 0.01 of a second. So we have significantly then reduced the time that's required in order for that to happen, because this is happening in parallel and we have split this array quite nicely. One thing that's worth just noting at this point is that the time operation gives 3 different values out. Real time, which is the time we're really concerned with, which is the actual overall time of execution. System times, the amount of time we're waiting for the kernel for kind of I/O operations and things like that. In these examples, it doesn't really matter. And then user time. That is the amount of actual CPU time that's been used across all the cores. So you can see that we've gone from 0.07 real time, 0.07 user time in our single threaded execution. So as you'd expect, 700ths per second of CPU time, and it took 700ths per second to run. We're now using slightly more CPU time, 800ths of a second, but we've reduced the overall time because obviously we're running that in parallel, so things add up and come together. One of the other things to consider here is, are there any more potentials for speed up? Are there any things in this code that could be slowing things down? So there's no possibility of race conditions because each element of the array is being implemented and worked on independently of the other ones. But there is a potential where, because we are updating arrays which are closely linked to each other in terms of memory space as we go through, we might find is that actually is slowing things down because we're waiting for blocks of memory to be released, to be put in. In order to test this, what we can do is we can use a temporary variable within that to test what happens. So if we go into here, let's create a temporary counter local to the thread. Starts as 1 because we know that it's 1 that goes in. What we're going to do here is we're going to multiply that up, and then once we finish this loop, once we've actually done the large amount of work that we're going to do, we're then going to set that back into our factorial array as a result. Unlike previous examples we looked at, there's no danger of race conditions here because this is updating. This is the only index in the array that's being updated by one thread. But what we're doing is, instead of updating the array in real time, we are using a single location in memory, a temporary variable which is local to this thread. We are then using that to multiply up, and we're coming in. Let's see if it actually makes any difference. .17, and you can see that there we go. It's made a slight difference. We're now down to unmeasurable time. We are now below 100th of a second in terms of execution. We're using 0.02 of user time. You can see that that's come right down as well. Purely because we're not waiting to update memory, we're able to go in, and this is something again we look at in more detail later on. But you can see here that we've very simply broken this out into parallel 4, and through the power and the speed of this, we've gone from an execution time of about 700ths of a second into less than 100th, and rounds down to 0 to less than, I don't know, 4,000ths of a second, 4.9 thousandths of a second in there.